Up until this point, everything that we've done at this house party has occurred at approximately the same temperature. Remember, people showed up at this house party. It was late afternoon. It was a nice Austin early spring day. People were enjoying themselves. It was going well. We had just gotten to the point where we survived a crash of the house party by 5 guys, the crash of the house party by 6 girls. But when it was all said and done, and it all settled back down, and what was happening over the rest of the late afternoon into the evening was that there would be 6 people holding hands and kissing in the back room, and out in front there would be 3 boys and 4 girls sipping tea and talking about the impending classes they would take that semester. Notice the important thing, we're at equilibrium. K is equal to 6 over 3 times 4 is equal to a half. K has somehow weathered lots of concentration changes and stayed at a half. What I'm now going to show you is going to be a big change for us. It's going to be the change in which we see that there is, in fact, something that makes K be a different value. Obviously, concentrations don't change K. You stress a system by changing the concentration, it gets back to K. Pressures don't change K. You change the pressure, it gets back to K. But it turns out that if you change the temperature, you in fact change K. And we understand this thermodynamically. We watched this play out all the time when we were doing the thermodynamics back in the fall, because if you think about it, if you put temperature into a system, you are in fact driving entirely different kinds of processes happening because of the kinds of energy that goes into the bonds. So under these circumstances, the likelihood that at equilibrium at some new temperature, everything's going to be exactly the same in terms of the relative ratios of products to reactants isn't going to be true. For example, as we'll be seeing coming up soon enough, if I've got some water and it dissociates to make protons and hydroxides, at one temperature, it dissociates to make a certain number of protons and hydroxides. But suppose I put a whole bunch of heat in. Now more of them are going to dissociate and make protons and hydroxides. So at that new higher temperature, with more energy in the system, I am making more products. Well, that more products I make at equilibrium is going to be a K value different than what I had at the lower temperature. So temperature dependence turns out to be a very important part of what we see when we look at K values. So my next 2 examples from the house party are going to occur at completely different temperatures. The same kinds of ideas are still going to rear their heads in terms of what's going on. By that I mean we're still going to have a stress that shifts us away from equilibrium, but we're still going to try to come back to equilibrium. It's just that it's going to be at a new equilibrium constant value. So here's our next case. It's getting near dawn, and it's suddenly gotten very cold. And because it's gotten very cold, people have decided that they need to snuggle more. What ends up happening to K? Well, the reaction starts to shift to the right. It's making more boy-girl couples. K has gone from a half to 4. Well, quite naturally, the system decides to respond to the fact that K has gone from a half to 4. And because it shifts to the right, evidently more of these boys and girls that were sipping tea out front are going to decide to come to the back room and hold hands and snuggle. When it's all done, K has to be 4. And there's the result. As I look at this here, there are now 8 boy-girl combinations in the back room. And there are 2 girls and 1 boy in the front. So 8 over 2 times 1 is equal to 4. Notice I haven't changed the number of participants. I still have the original 4 boys and 4 girls. I still have the gate crashing 5 boys, the party crashing 6 girls. So the same numbers of boys and girls are there. So the conservation of mass is there. And yet I've been able to find a way for K to get to this new equilibrium constant value of 4 by making sure that the appropriate ratios of front room to back room happen. This is the first example of temperature dependence of K that we'll see. Let's look at another one. I've just shown you what happens when the temperature got colder and the reaction shifted to the right. Guess what? We're about to see that when it gets hotter, the reaction is going to shift to the left. So we fast forward to late afternoon. People have slept through the morning. It was cold, but like happens oftentimes in Austin, it gets warmer and warmer and warmer. These people woke up late afternoon the next day from this party. It had been a bad day. Got really hot. They wake up, they look at this person they're sitting next to, and they're saying to themselves, geez, what am I doing here? I think I need to go out in the other room. I need to stop snuggling. Suddenly, K is an entirely different value. In fact, K now has become 1 over 72. Now that K is 1 over 72, I have to make this equilibrium reroute itself so that I get this new value. Isn't it kind of interesting? I've seen K be 3 different values. I've seen K at a pleasant temperature be equal to 1/2. I've seen K when it got cold be equal to 4. And I've seen K when it got hot be equal to 1 over 72. This is quite a normal sort of phenomenon to see. It's this nice sort of consistent change in K as a function of temperature. But regardless, the system doesn't have much ability to respond other than to say, whatever you say, I've got to get to my new K value. You put on the stress of making the temperature hotter and making K now 1/72, so the system reorganizes itself. When it's all done, there's only one boy-girl in the back room. In the front room, I have 8 boys, I have 8 girls, and I have 9 boys. And as a result, I have my K now equal to 1/72.